So yet again, we've got a new layout for the board. So for that, I apologise. Let's get on with lesson 10, or tutorial 10, which is about dynamically size arrays. So in the previous tutorial, we looked at creating arrays, and we saw that you could create arrays of any size and any dimension. We also saw that you can create the size of an array using a variable as input to the sizing format. And so you might think, well, we can already in a way create a kind of dynamically sized array. But the problem with that is we can't change the size of the array once we've created it. And to give an example of why we might want to do that, imagine if we were creating a program to draw graphics, something like Inkscape, or I don't know if you're familiar with that, or CorelDRAW, or one of these kind of programs. And what we need to do is every time we create a new line or a new circle or whatever, some kind of new element in the drawing, then we're going to store that in memory, and like before we save it to disk, we're going to have a representation of all of that in memory. Now we don't know how many lines a person is going to draw in advance. We don't know how many circles they're going to draw and how many elements they're going to add to a drawing. So we can't a priori allocate that memory. That we could say, oh well, let's make space for 100 lines. And what if they draw more than 100 lines? We can't then add more, because we've already, with those kind of array declarations, we can't change the size. So dynamically sized arrays are very useful for creating memory for arrays when we don't know in advance what size we need and when that size can change. Another time they're useful is in passing parameters around. For the way that a statically allocated array that we saw in the last episode is allocated, its scope is whatever the block is that it was declared in. So if you declare it within inside a function, its scope is only that function. As soon as you return from that function, that memory is no longer available. That array is no longer available. You can't pass it around because of that. You can pass it around if you put it in the outermost scope, globally, and then you could pass that around, but that's kind of a special case. So what we need is dynamically sized arrays. And for that, we're going to have to look at memory allocation. So we're going to have to use malloc. We're going to do a separate talk on malloc, and we're going to do a separate talk about pointers, but we're going to use both of them in this tutorial. But we're going to use them specifically in the context of allocating arrays. And this is a kind of gentle then introduction to them, because there'll be a certain pattern you can follow in order to use them within the context of creating dynamically sized arrays. So let me just go ahead and give an example of creating a dynamically sized array. So let's go ahead and declare our first dynamically sized array. First of all, we're going to have a variable which is going to store the size of it, because when we're creating a dynamically sized array, typically we're going to want to pass the size in as a variable. Otherwise, why are we using a dynamically sized array? So we'll have the first variable, which is going to be called a_size. And let's assume that it's 10. So there's going to be 10 elements in our array. Now we're going to declare space for the actual array itself. So this time I'm going to call the array A again, but we need to put before A an asterisk. And what this means is the association of the asterisk is actually with int, because we're talking about, the asterisk means a pointer. So the actual type here, the asterisk is a type modifier, and it's modifying the type int to say that this is an integer pointer. But typically you'll see people put the asterisk next to the A, because the white space here, apart from, doesn't actually matter. So what we have here then, we're saying that A is an integer pointer. And what that means is that A points to an area of memory that contains a sequence of integers. And what we usually might do is give it the initial value of null, which means it points nowhere. And this null value is understood by other functions that we might pass this pointer into. So the moment it points nowhere, and we haven't provided any size or anything, it's just a pointer to some, essentially an integer array that doesn't exist. So now we need to allocate memory for that integer array. And the way we do that is as follows. So we would say A equals malloc, so that's the function we call memory allocate. Then we're going to have our size, A underscore size, times size of int. And then there's two brackets there to close off the size of and close off the malloc call. So if that isn't clear, I'll just write what's in the bracket there. We've got A size times size of, one word, int. That's what's inside the bracket. So what's happening here is we're saying allocate a certain number of bytes. So malloc takes a number of bytes to allocate. So how many bytes do we allocate if we want to store a size number of integers? Well, we know it's got to be a size times something, but how many bytes does an integer take up? Well, it might be 4, it might be 8 bytes. You know, we might be on a 16-bit architecture. Could be a couple of bytes. We don't know. So what we use is this operator, which is part of C99, called size of. So we pass in int to size of. And then that tells us the number of bytes that an int actually takes up. So then we have the number of bytes that the int takes up multiplied by the number of elements, which is the size that we want, which gives us a number of bytes, and then allocates the memory for that, and then assigns that to A. Now you'll sometimes see people saying, as you often do in languages like C, quite like sort of low-level languages, they'll be saying you don't need to use the brackets for size of. It's true. Size of is a unary operator, so you don't have to use the brackets. You can put a space and then an int. But at the same time, you can also put the brackets, and that's a valid way to do it. And I think it's a lot more readable with the brackets. You just often see this, if you hear anybody kind of giving you this kind of like, you should be doing it this way. You must be doing it this way because why are you using the brackets? You know, this is just bonkers. Just ignore it. Just ignore it and go on and write your program and enjoy programming, and just ignore those people because they're kind of trolls in a way, language trolls. So anyway, you can use the brackets around size of, and almost everyone does actually when I've seen it. But you don't have to. So then that allocates our 10 elements of size integer to A, and we've got a piece of memory there. That is now the same, or the equivalent, in terms of allocating the memory, as if we had declared an array statically with 10 elements. So we can now access the array elements as normal, like that. That would be the 0th element of the array. So we can do that all the way up to 9. So A9, which would be the 10th element of the array. So that's quite straightforward. That's the allocation of the array. So that's how you would create it to begin with. Before we resize it, what we're going to do is show an example of using that. But one more thing I want to say. Whenever you allocate memory, whenever you call malloc, you always need to have a corresponding call to free the memory associated with A when you're finished using it. You don't have to if your program just ends, because obviously then the program's not taking up any memory space. But it's good practice to always free any malloc that you allocate. Any memory you allocate, always free it. Otherwise you can get what's called memory leaks, where you're not freeing your memory and you keep allocating it and you run out of memory. which is something you don't want to do. And so to free a previously allocated pointer A, you just use the function free, and then you pass in a pointer. That has to be a pointer, and that will free it. So let's look at an example of that, and then we'll look at how you could resize something you've already allocated. So this, you only allocated space for 100 lines on your drawing, and now they want to do the 101st line. Oh, we better allocate another 100 space for another 100 lines, that kind of thing. We'll look at that next. Let's look at what we've just done now. Alright, so we've got a file called hello-dynamic.c, and in our make file, again, we've got the classic of just a single default that says hello dynamic. Now, what you'll notice is that we're including two header files. The first one is called standard lib. This is where malloc, the malloc function, resides. It used to be in malloc.h, but now it's in standard lib. And we're including standard IO so we can do our printf and so on. So let's go ahead and do exactly what we did on the board. So the size of our array is going to be 10. We're going to start by allocating or declaring an array called A or an integer pointer called A that has the value null. So it just points nowhere. So it's just nothing. There's no memory allocated for it. And as I said, you can do it like that if you want. You can do that if you want. I tend to do it like this. Sometimes I do it like this if I'm returning a value. You'll see both variants, and just do whatever you feel comfortable with. So that's declared an array called A, or a pointer to integers, that has nothing. And now we're going to do the memory allocation. And what we're going to do is we're going to do this properly. So first of all, we're going to call malloc with a size times size of int. So that's our memory allocation. Now the memory allocation can fail. If we try and allocate 1 billion trillion bytes, we're probably not going to have enough memory. If you're watching this in 2050, you probably can, but at the moment you probably can't. It's very rare that memory allocation will fail on a simple program, but on something like a server where you're allocating tons of memory for streaming things and so on, then it could definitely fail. You could even run out of swap space. So we want to check if it fails. Now if it fails, malloc will return null. So we say if a equals null, oh no, we're gonna fprintf. Now I'm introducing a new function here, fprintf, which means printf but to a file. And we're going to print to a file called standard error. This is, again, you'll see this on the console. It will print to the console, but it's a special error stream file that can be separately redirected on the console. And we're going to say error allocating memory, or mem, because I don't want to go in a new... Right. Now I've got enough space. There we go. So if that happens and we can't allocate the memory, we're going to call a function called exit, which is part of standard lib. And what we pass to exit is the return value. And we want that to be 1 actually, since we're saying that 0 is a successful exit. So if we can't allocate the memory, we exit. We print out an error message and we exit. If we can allocate the memory, then malloc now contains, A now contains space for 10 integers. So what we can do is, sorry, I should use A size there, shouldn't I? Let's fill A up, as we did before. I times 10, let's say. And then let's print out A to check that we've done it. Say like this. And once we've printed out the array, we then, like I said, we want to make sure we free A. So we free the memory associated with A. And then we return. By the way, exit will close any open file handles and clean everything up for you. if we exit at that point. So we don't need to free before we exit. Can if you want, but you don't need to. And that's essentially it. So let's compile that. Got a couple of errors, I'm just going to leave them in. Yeah, well there we go. I don't know why I didn't put an assignment operator there. That's the first one. In fact, done all the errors of that. There we go. So let's run it. So it's not particularly exciting. It just looks like one of the examples that we gave in the last episode. We've essentially just allocated an array of size 10 and then assigned values to it and printed them out. But hopefully you can see that it's not anything to be particularly scared of. We're just using the function malloc and we're allocating some memory. If you want to know about malloc, you can of course go do your man malloc. On FreeBSD they're using gmalloc, but it'll just tell you all about it. The malloc function allocates size bytes of uninitialized memory. So it's worth pointing out that the memory again is uninitialized. It could just be garbage. It could have anything in it. And then it's up to you to initialize it. There's another function called calloc, which initializes it with the value 0. Everything would have the value 0, all of your memory. Every byte, that is, would have the value 0. Hopefully that wasn't too painful. It's pretty simple, right? We just call malloc to allocate memory for however many elements times the size of that element. So size of int, size of double, size of char, and it'll allocate that memory. And then we just address it like a normal array. Let's look at resizing. Resizing an array, because that's one of the powerful aspects of using dynamic memory allocation. So if we've allocated A, so we've done the setup, and then we call A equals malloc, whatever it is, A underscore size times size of int. Now we've got a pointer A. If we want to reallocate that with something bigger, so perhaps A size changes size. So it doubles. And we then want to make sure that A has twice as many elements, or space for twice as many elements. What we do is the following. We use a function called realloc. Now realloc returns a new pointer. So we can't just assign it to A. Most of the time we can actually, but strictly you should not. Because if the reallocation fails, what it will do, it will overwrite A with null. And also, the reallocation might have to move the memory that was allocated somewhere else in memory and return a new pointer because it's moved. Because it might not be able to fit, it might not be able to just expand the space that it had to fit your new size. So we need space for another pointer. So we'll call it temporary. Temporary names are always one of those things where it's, I don't know, I hate using that name, TMP or whatever, but it's always quite difficult to think of a good temporary name. But anyway, so what we do is we say TMP equals realloc followed by a pointer to the memory that we're trying to change, so that's A, and then the new size, which of course is A underscore size, and I run out of space, but that, imagine this is all on one line, times size of int. So in the realloc, let's just write down here what the parameters are, so it's clear. The first parameter is A, the memory we want to reallocate. And then the new size is the second parameter, which is A size times size of int, which is the same way that we sized the initial allocation. Now the pointer from realloc is now in temp, but we want it to be in A. And what we do is, first of all, we check whether temp is null or not. So we're just going to rewrite the realloc line. So temp equals realloc. We're reallocating A, and it's going to be A underscore size times size of int, semicolon. So now that temp has the return from realloc, if the reallocation does not work, then temp will be null. So we then need to check, is temp null? So if temp equals null, equals null, then, you know, clean everything up, exit maybe, or in your program you might want to say ran out of memory, close some other programs and try again. I don't know, you know. Maybe the program would take some other action. Maybe it would then serialize some stuff to disk to free up some memory, free up some of its own memory that it's using in order to get more memory. But anyway, if it didn't work, we do that. If it did work, then imagine we're down here, then we'll just say A equals temp. By the way, if this pointer is moved, realloc will free the previous version of A. So say A was in address 57 in memory, and then we double the size of A in our realloc, and because it won't fit in where address 57 is, because there's some other memory allocated, and it moves it somewhere else, it will copy the contents of A into the new location, it will give us the new size, and it will pass that back, and it will free A as well. So we don't have to worry about freeing A. We just assign the new pointer to A. A is now a resized array, and we can address it again as normal. Let's take a look at an example of that just to make it really clear and see that it isn't really that complicated as it might sound. So I've created a new program called Hello Realloc. So first of all, let us create A. And I'll tell you what, we're just going to malloc it straight away. We're going to have our A size here equals 10. There we go. If A equals null, I'm going to print out error allocating memory. And exit. You know, you might want to do something else there or print out a more descriptive error message. So we've got A. Tell you what, we'll fill up A with something that we can see. So same as before, really. I times 2, 10 maybe. There we go. And should we print that out? Yeah. Now we're going to get to our realloc. So we need some space for the reallocation. We'll call it temp. Let's make it null. Just get in the habit of making any kind of pointer null whenever you declare it, define it the value null. And we're going to say, of course, A size needs to change. Let's call it new size. So we'll have another variable called new A size equals, we'll give it the value 0 there. But we'll imagine that the new A size is going to be equal to A size times 2. And now we want to reallocate A. So we call temp equals realloc, and we're reallocating A. We've got the new A size times int. So that's just in terms of number of elements. So it's still times that. And then we say if temp equals null, and we can print out an error here. Error reallocating A. Now, what do we want to do in this case? Let's just imagine we exit. You know, we just can't function in this case. Let's just pretend that. Otherwise, we know that temp is not null, which means that the reallocation was successful. So we say that now A equals temp. And A now points to the newly reallocated memory. And just out of interest, we'll print out all of the elements again, and the new elements. Because realloc will copy, when it creates the newly sized array, it will copy whatever the old sized array was. Once we're done, we can free A and return 0. And compile that and run it. And we can't really see what's going on, so we'll just pipe that into less. Actually, let's add something in here before the realloc. Reallocating A, so we can see what we're doing. Done. Compile that, pipe it through less again. So first of all, we allocated memory for A and printed it out. We then reallocate A, and then let's have a look. We're now printing out the new size, which we know is twice the original size, so it's 20 elements. And the first 10 are unchanged, and then the next 10, in this case they've got the value 0. They don't have to, it's uninitialized memory, they could have any value. But you can see that the original elements are unchanged. So we've just got 10 new elements that we can now use. So our reallocation was successful. So that's memory reallocation. Alright, you've seen memory reallocation, and hopefully you can see it's not really that difficult if you just follow the pattern. So what we'll look at now then is passing arrays to functions. And what we need to do is we pass the pointer. Let me show you an example. So imagine we've got some array called A that's been dynamically allocated, so it's an integer pointer. And we want to pass it to a function. Let's define the function. What the function is going to do is just print out the elements of the array that we pass to it, and it's an integer array. And we'll call it PA. It doesn't return anything, so we're going to say void is the return value of it. The function name is PA. It takes 2 arguments. The first one is an integer pointer. And just to avoid getting confused with what we've got in the main body, where we're calling the array A, we'll just call it B. We can call it A, but just to show that it's different, to make it clear that it's different. And then we can have a second parameter, which is going to be the B size. And because I haven't got enough space, I'm just going to call that BS. So that's our function prototype. So the function PA takes 2 arguments, a pointer to a bunch of integers, or an integer pointer as it's called, and an integer called BS, which stands for the size of B. We need to know the size of B because it's not part of this structure, right? This is just a whole bunch of integers in a row. There's no size information there. And of course, within this function, we could do something like a loop or whatever and say for int I equals 0, I is less than BS, I plus plus, and we could just print out perhaps just one on each line, bi. And the function doesn't return anything, so we just end there. So that would be an example of a function which takes an array and prints its elements, an integer array. And so to call that, say we already had our A here, and we've done our allocation and so on, blah blah blah. We then just call PA with A. Pretty simple, right? Let's take a look at that. So let's look at how to pass an array into a function. So we've got a file called arrayToFunction.c over here. So first of all, the function that we're going to pass the array into returns nothing. We're going to call it print array. In fact, we're going to call it print int array because that's what it actually does. And it takes an integer array, we'll call it b, and it takes an integer called b size, which is the size of it. And then it's pretty simple. It just prints out each element of the array. It's quite hard to actually, I just realised it's quite hard to speak and then type something at the same time. So what we want to print out is, basically this. The index and then the actual element. And that's it. That's all it's going to do. Now down here, we're going to have an array called A, which is initially null. Actually, there's no reason for it to be initially null. We'll just malloc it straight away. And it's going to be, our size is going to be 10. So it's A size times size of int. That's it allocated. I'm just going to put these in now, so we don't forget. And we need to populate our A with something, otherwise we're not going to print anything out interesting. So let's loop through and go through here. And we'll allocate to A. We'll just make it I times 100 this time. Then we're going to call print int array with the name of our array and its size, and see what that does. There you go. It prints out the array as we expect. So that's how we pass an array in when it's a pointer. So just something about this. This is actually an integer pointer. Now, an integer pointer, in the case where it's a single integer and in the case where it's a bunch of integers in a row, the integer, when it's a single integer, that's just a special case where the array essentially has a length of 1. All this really means is when you allocate an integer pointer, it tells C that when you put an index into it, like this, it tells it that it should increment by the size of an integer for each index you put in. So for 2 index, if this was 2 or whatever, then it would be 2 times the size of an integer relative to that memory address. So it's just essentially a pointer to an integer rather than a pointer to an array of integers. But we happen to have put an array of integers there, if you see what I mean. Don't worry if that was confusing. So there you go. That's how you can pass an array into a function. So while we're at it, let us now return an array from a function. So let's create this function. So it's going to return a pointer to an integer. And we're obviously going to return a block of memory, or a pointer to a block of memory that's got a whole load of integers in a row, therefore that are an integer array. And we're going to call it create array, and we're going to just pass in one parameter called a size. In fact, no, we're going to call it length, just to be verbose. And this is going to create an integer array. So let's call it actually create int array of that length. So what we can do here is we'll create our array, length times size of int, and what we'll do is, if this failed, this memory allocation failed, and this is null, we don't really care because we'll just return null. So if a equals null, we return null. We're just going to return a, right? Essentially just returning null. And we'll leave it up to the caller of this function to check that this returns an actual valid array and not null. So it will have to deal with the error. So if a is not null, then we're going to populate it with something. Oh, it's called length, isn't it? And we're just going to this time fill it with I times 1,000. Kind of running out of different things to do. Once we've done that, we're going to return a. Now, we can now go and change this code because we don't need to do this kind of population part anymore. We can just say int a equals create int array and then the size of our array. We should probably check whether or not this is null, you know, because we said that we would deal with that. But let's just, for the sake of brevity, let's leave that out for now. And just run it, and there you go. So now we've created an array via this function which passed back the memory and stored it here. We then printed that out by passing that into another function called printIntArray, which then printed it out. And of course, it doesn't matter what we call these things, these names are only valid within the scope of these functions. So length is only valid within the scope of this function, b and b size are only valid within the scope of the function. That's the names. But because we're pointing to a block of memory here, we can also change the array. So we could have another function like void change array, and let's call it double array. It's just going to double the elements of the array, and it's an integer array, so we'll call it double int array. We need the length of the array. We're going to call it a size, and then what we're going to do is we're going to go through the array and we're going to change the values. So AI, and we're going to do this, times equals 2. We can refer to those values as if they were normal. And that's it, we don't return anything. So this time we're going to print the array out, then we're going to call double int array with our array, and we're going to print it out again. And we're going to print doubling array here. Let's just compile that and run it. And there we go, we'll print out the array as we initialized it. And then we call this doubling array function, which doubles the elements. And then now we print out the doubled array. So there, hopefully you can see now that you can pass around a pointer to an array, or an integer pointer, and you can pass it into functions, you can return them from functions. But remember, wherever you allocate memory, so in this call to malloc up here, which is within this call to create int array, we still have to free that at some point. Otherwise we could risk getting memory leaks. In this program we're not going to get them because we immediately exit after, but remember to free any memory you allocate. So now you know how to pass a pointer to an array, to an integer or a double or a char, pointer to a piece of memory that is an array. You know how to pass it between functions so that essentially it doesn't matter where it's declared or defined, the scope of your arrays can now be the scope of your entire program. We're going to look at a couple more things. We're going to look at how you can pass a statically declared array to a function, because you can do that. And then we're going to look at declaring a two-dimensional dynamic array. So to talk about the first one, how to pass a statically declared array to a function. Before we do that, let's just look again at the dynamic creation of an array. Int pointer, so integer pointer a equals malloc, and then say it was 10 times size of int. Let's just think about what's happening here. I know this may be, I think it's worth doing this. So say the size of an integer is 4 bytes. 10 times size of an integer is going to give us a block, and let's have a square just represent a byte. So that's 1 byte, that's the second byte, and so on. The address that's returned by malloc is this address here. So that when we index a with 0, we get 0 times the size of an int added on to this address, which gives us this first element. When we index it, so say we do an A1, we get 1 times the size of an int added on to this address, which takes us to here. So there's two things that happen when we allocate the array, and I want to try and separate them out so that you can really understand what's happening. One of them is that a piece of memory is allocated, which in this case is 4 bytes times 10. So 40 bytes has been allocated. That piece of memory that's allocated does not have any inherent type. The way that a type comes into this is to say that that address is an integer pointer. So that's how then the compiler understands how to do this arithmetic. Because it's an integer pointer, it knows that if we want index 1, it multiplies it by, say, 4 bytes, assuming our integer takes it 4 bytes. It might not, right? Might be more, might be less, depending on what type of machine we're on. We don't need to know because we use this size of operator. But that's where this int comes in. It's just telling us essentially the size of each of the elements in this indexing method. And if we had a char pointer here, that would be 1 byte. And then, so if let me draw a char pointer just so you can see. If instead of an int, we allocate a char, the char is 1 byte. So, and we know it is actually, so we don't normally have to do size of char, but if it helps it more readable, do that. In this case, if we do a 0, again, we just add 0 times the size of a char to the address, and that gives us the first index. But this time, of course, A1, 1 times the size of char, well, char's just 1 byte, so that's just going to take us here. So what I'm trying to show you here is that whatever the size here is, that is what determines how we index into the block of memory allocated by malloc. So what I want to say now then is how you would create a pointer to a statically declared array. So say we statically declared an array called A, having size 10, we can actually create a pointer to that using the ampersand operator. So we're going to call this AP for pointer to A or A pointer. And we draw an ampersand A. And that ampersand operator takes the address of A. Sorry, that's a pointer. So we get the address of A. And if you think about it, what's happening here is this A is actually created on the stack by the compiler, or at runtime if it's a variable sized array. But this A is just going to have a piece of memory. It has to, right? I mean, that's where it's stored. It's stored in memory somewhere. And when we take the address of it, we're just taking this address here, where that block of memory is, which means that then AP points there. And then when we do something like AP1, we know how to index into this. Because it's an integer, we take the address of AP, multiply it by the size of an integer, 1 times the size of an integer, which would take us to here. So that would be AP1. So we can take the address of an array that's been statically allocated. Now that's useful because that means that we can then pass that into a function and modify that array. That only really makes sense if the array is declared outside of the scope of the function. So say it's in your main part and then you want to modify it inside a function. Let me give you an example of that so that you can see. So the first thing we're going to want to do is declare a static array, and we're going to populate it via a function. So we're still going to have a function again, which is, I don't know, change int array. Takes a pointer to an array and an array size. And it's very simple. It's just going to loop up to a size and initialize A as I times 100, just so we can see what it looks like, right? So in order to pass that in, we can use the address operator to get the address of this array, and we'll call that AP. So this is a pointer, an integer pointer, and we just do this. So now what we can do is we can now print out A. So we'll go through A, and we will print it out. And that's it. Notice we do not have to free this pointer because we didn't allocate that memory. That memory's been statically allocated here. Let's have a look. What's wrong here? Yeah, okay. So sometimes when you do this, because this was an integer array of size 10, that is classified as a separate type, even though, it's not really. So this is given, Clang has given a warning saying incompatible pointer types, initializing an int pointer with an expression of type int pointer of size 10. But we know that we could ignore that warning, because the logic that I've given you is sound. We are allowed to do this, but to get rid of that warning, we cast it to an int pointer, just to explicitly say, yeah, that's what we mean. It is an int pointer. Cast it to an int pointer. What's the other error? Oh, yeah, A size doesn't exist here. That's true. Let's recompile that. Oh, there's still another error. I've put 2 commas in here. Okay, so let's run that. And what we've got there is complete garbage. And the reason we've got complete garbage is because we haven't actually called our function change int array. But that's a good kind of serendipitous example there
because we haven't initialized it. So now when we do pass it into the change int array, you'll see that it really does change it. So we're passing in to our change int array the pointer to the array and its size, which is 10. Let's run that again, and there you go, it's what we expect. So even though this was statically declared, we can take its address and then pass that address into a function which takes an address to an integer, a pointer to an integer, and modifies it. And that will then actually be addressing this. So it takes the memory address of this, wherever that actually is, when we do this. Don't worry too much about this stuff. We're going to cover taking addresses and dereferencing pointers and so on in a special episode about pointers. But I just wanted to cover it because I think some of you are certainly going to be able to follow this and understand it and make use of this stuff.
So you've seen now how to pass around a pointer to a statically allocated array and use it as if it was dynamically created. You can't free a statically allocated array, so don't try. You'll get an error if you do. So the last thing we're going to look at is declaring a two-dimensional array dynamically. This is probably the most complicated thing that we've done so far in the tutorial series. And this is why I was kind of trying to be reasonably thorough on talking about the way that the memory is allocated for an integer array. Because I want you to start thinking about pointers. And when we have a two-dimensional integer array, we need to use pointers to pointers. Let me explain this. So last time we said that if we had an integer array, and let's assume that we've got a few of them. So we've got A and B and C. And imagine that we then allocate memory for them here. What these look like, if we look at the memory address at A, we're going to have our bytes in memory, assuming again 32 bits per integer or 4 bytes per integer. And our A will be like this, our B will be like this as well. And our C will be like this. So quite straightforward so far, right? So A, B and C all take up space in memory, or they're addresses to space in memory, where we're putting integers. If we want a two-dimensional array, so say these were 3 rows of a two-dimensional array, essentially what we want to do is we want to index into here. So if we could put A, B and C into another array, so say we had an array called D, and if we could do something like this, so what D actually looks like is A, B, C. Then we could index into this by doing something like D 2 2, and what that would do would first of all give us the second element of D, which would be 0 1 2, which would be C. So we'd go to here, and then we'd take the second element of C. So we'd go 1 2, and that would be where our second element is. We'd have some going out here. So we want to actually do that. And in fact, we can do it like that. But whereas each of these A, B, and C is an integer pointer, what we're actually pointing to in each of these cases is a pointer to an integer pointer. So each of these A, B, and C needs to be the address of A, B, and C, which is the address of a pointer. So it's a pointer to a pointer. Let me try and show you that in code to try and make that more clear. And then I'll show you a pattern just for allocating a two-dimensional array, so you don't actually have to worry about this stuff.
So what we're going to do is start by creating a function which is going to create those arrays, integer arrays A, B, and C. So it's going to return an integer array. It's going to be called createIntArray, and it's going to take two parameters in this case. First of all, the length. I'm going to just shorten that to len, and it's going to take a multiplier, and you'll see what that's used for in a second. And all this function is going to do, first of all, it's going to allocate a piece of memory for the array. We're not going to worry about checking for errors at this point. But remember to do that when you actually write your programs. We'll just assume that's worked. And now we're going to populate the array with some values. And we're going to say that it's equal to I times the multiplier. Just so that we can, from outside, in our main function, we can initialize our arrays with different values so we can tell them apart. Now once we've initialized it, we return it and we're done. So in main, we're going to declare our three integer arrays, and we're going to use the function createIntArray to create them. And let's say that they're all length 10. And for A, the multiplier is going to be 10. For B, the multiplier is going to be 100. And for C, it's going to be 1,000, just so we can tell them apart. Right. Now, those three arrays have those values in. We're familiar with this. We've done this before. We did this in the previous examples. So now what we want is another array which essentially stores references to those arrays. So we're going to call this the array pointer, essentially. And it is a pointer, the type is a pointer to an integer pointer. And I'm going to explain on the board what this looks like. But let me just show you. We know we've got three. We've got three of these things, and they're the size of an integer pointer. Each of one of these is an address, which is an integer pointer. That's what we want to store. And what we can say then is, now I'll just do this explicitly. We could actually have statically declared this array, but we'll do it dynamically. This actually equals A. The second element equals B, and the third element equals C. And the reason I want to do this is so that then we can now iterate over both. So we're going to say I equals 0 up to 3, and then within that we're going to go j equals 0 up to array len. I'm going to print out, so we're going to do printf array pointer, and we're going to have I, j, and then I'm just going to put this on a new line, like that. And of course, before we exit, we need to free these things. So we'll have to do two things. We've got to free both this thing, which was dynamically allocated as a pointer to pointers, and then we need to free A, B, and C. But that's our program. Let's just see what that does. There's an error. Everyone makes mistakes. It's on line 25. Yeah, there we go. I've just put I plus for some reason. Here we go. So let's run this now. Can't really see the whole thing, so I'll pipe it through less. So at index 0, this is our first array. Remember, we allocated array A with this multiplier 10, so each of the indices is multiplied by 10, that second index. At index 1, we've got our second array, and at index 2, we've got our third array. So I hope that you can see that we can now create an array which holds addresses of other arrays, and then we can index them like a two-dimensional array because of that. And that is how we create a two-dimensional array. I will show you a generalized pattern for this, but I just want to explain on the board now what's going on.
Alright, so let me try and explain then what's going on. So our integer pointer A is a memory address. So that memory address itself will have a size. So on a 64-bit machine, it will be 64 bits or 8 bytes. When we go to that memory address, we know that we've got our integers, which we'll assume are 4 bytes, and they occur, in sequence at that memory address. But this is just a memory address. And then we interpret what's at that memory address by looking at the pointer type, or C does. So then, because the pointer type's an int, we can then index into that memory address, and we know that the index multiplier is 4. But A itself is just a memory address. So a memory address on a 64-bit machine has 8 bytes. So once we've got our arrays, this AP is a pointer to an integer pointer. So when we allocate it, we get this block of memory. And remember, the block of memory, before we interpret it, is just a block of bytes. But what we want to know is what happens when we index this. So when we put in an index. Well, what we're doing here is we're storing in these addresses. And these addresses are 64 bits, they're 8 bytes long. So this is where we put the first address, this is where we put the second address, and this is where we put the third address. So A is here, B is here, and C is here. That's the addresses of these. And then how does C know how to interpret this? When we do something like AP00, how does it know what to do? Well, again, it just needs to look at the type. So it looks at the type, so it looks at the first 0 and says, well, what we have is a pointer to an integer pointer. Well, an integer pointer itself is 8 bytes long. And the pointer to that is just the memory address of this. It's just the start. So we go to the start, and then we say, well, oh, it's 0. Well, let's take 1 then, because one's a better example. And it's 1 times the size of an integer pointer. Well, an integer pointer, in fact, any pointer will be 8 bytes long on a 64-bit machine. So it's 1 times 8 bytes, which then takes us to here, which is what we expect. We then take that address, which will take us to here, or where the memory address would be, and then we say, well, how do we then interpret this next one? Well, this was a pointer to an integer pointer, which means that this next thing is an integer pointer. So we need to multiply it by the size of an integer. So we multiply 1 by the size of an integer and we get here, which is how we get there. So the first kind of indexing operation on this gives us a pointer to an integer pointer. And a pointer is 8 bytes long, so we index in with 8 bytes. Then we know that what we're looking at is an integer pointer, and we need to index into that. And to index into that, we need to look at what it is, and it's an integer. It's indexing in. It's a pointer to integers, so we multiply by the integer size. I'm going to go over this again in pointers, but I just wanted to try and cover that a little bit. Even if you don't completely understand what I've said, maybe it's trivial to you, maybe it's obvious, but if it wasn't, don't worry. Don't worry about it. It's okay to be confused if you are. It's good that you've seen it, and then in the future we'll go over this again, and hopefully it will make more sense if it doesn't now. So the last thing I'm going to do is just show you a pattern for allocating a two-dimensional array. So at least if you need to dynamically allocate a two-dimensional array, you can without having to really understand what's going on.
So I've created a file called creatematrix.c because a 2D array is a matrix. That's another name for a 2D array. And we're going to create a function that creates a matrix, a two-dimensional integer array matrix. So what it returns is a pointer to an integer pointer. And it's called create int matrix. And we're going to take two parameters. We're going to have the height of the matrix and the width of the matrix. Or let's use something else. We might say the number of rows of the matrix and the number of columns of the matrix, just to be consistent with the matrix notation. And the first thing we want to do then is allocate space for the pointers to our rows. So we say that our matrix M is going to be malloc, and it's the number of rows times size of integer pointer, because each entry is an integer pointer, right? Each row entry is an integer pointer. Then of course we need to construct each of the actual rows for the elements of each row, or the space for the elements of each row. So what we can do is we say, while I is less than the number of rows, mi, so in the ith index of m, we now allocate number of cols times size of, and it's int, because we're allocating enough space for that many integers in that memory address. And that is actually it. That is our matrix created. So then we can just return m. Now what we can do here is we can create our matrix. And we can make a 10 by 10 matrix. And we need to populate it with something. So actually what we'll do is we'll say number of rows is 10, number of columns is 10. And what you'll notice here, of course, is I'm using actually the same variable names here and here, but they're in different scopes, so they're not interfering with each other. So that creates our matrix M. And I'll tell you what we'll do is we'll create a void function called freeInt matrix. And all we need to know is what the number of rows are to do that. And all our free function is going to do, it's going to go through up to the number of rows, and it's just going to free each row. And then after it's done all that, it's going to free M itself. Oh, of course it needs the matrix. otherwise it can't free it. So that will free a matrix that we've previously allocated. So we'll put that at the end. So what do we want to do? We create our matrix. Let's populate it with something. We'll use j is less than number of cols. And we're going to populate it with mij equals I times j, perhaps. And then we want to print the matrix. So let's create another function to print the matrix. Print int matrix. So it takes an int matrix. We need to know the number of rows. We need to know the number of cols. And what we're going to do is we're going to loop through again. So I'm just going to copy this because I'm lazy. And we're going to print out. We're not going to print out any indexes or anything. We're just going to print out nij, and then at the end of each column, at the end of each row, we're going to print a new line, so that we'll see it in kind of matrix form. So we've initialized our matrix. Now we're going to call print int matrix. And if the magic incantations have gone correctly, there's an error. How frustrating. N. Very annoying. There's another one as well. So as you can just see that. Too few arguments to function. Correct. We can't just call free int matrix with an m. We need to know the number of rows, which is what we said our function prototype was. It takes the matrix and the number of rows. So we need to free each row. Right, there we go. That's done. So let's have a look. That's the output of our matrix. Annoyingly, it's not aligned, but if you remember back from our printf tutorial, or very start, we can actually specify a width modifier there so that we pad it to width 2. And there we go, that's our matrix, and this would be index 9, row 9 and column 9, and we just assign the multiple of the two after we created our matrix, and that's the correct value, 81. So there you go, that's how you could create, populate, and then destroy a two-dimensional matrix dynamically. And of course we could go through and we could change the length of any of these rows by reallocating that particular row. We could even reallocate the number of rows, so we could add on another row, and that would just create a new pointer to an integer pointer. But I'll leave that up to you to try and create a function to resize an array.
If you've got through all of that, well done. I know that was a little bit heavy, but it's really useful to know about arrays, and don't worry, this stuff will just become more and more familiar and become very straightforward with time. Next episode we're going to look at character arrays, or strings, which are just arrays of characters. Now, in all the examples we used an integer array, but you could have replaced the int type keyword with double or any other type, and the behavior will be identical. We just get different sized arrays to store that type of element, like a double or whatever. Anyway, I hope that was useful, and I'll see you next time.